The Indian Association of Structural Engineers, also known as IAStructE, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. IAStructE is registered under the Societies Registration Act 21 of 1860. IAStructE is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural engineering fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IAStructE has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Kumar Ghosh, late Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Manoj Mittal, Professor R. Pradeep Kumar, and Shri Alok Bhaumik as its president. IAStructE is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IAStructE has collaboration with various international professional like-minded associations and institutions like IAStructE, UK and FIB for strengthening global connections and professional exchange. IAStructE's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IAStructE endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IAStructE is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs. Seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IAStructE's activities are widely appreciated and known for quality technical contents. IAStructE is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines, monthly newsletter, and Crossfall, a unique quarterly newsletter that confidentially reports structural failures and the lessons learned from them. IAStructE's publications are becoming popular with time. IAStructE has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IAStructE started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. Reaffirming its commitment to professional excellence, IAStructE launched the accreditation program in 2023. This flagship initiative empowers practicing engineers to evaluate their competencies, identify growth opportunities, and strengthen the foundation for sustained professional success. IAStructE is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide hand-holding to the budding engineers. Joining IAStructE offers exclusive resources, mentorship, and networking with industry leaders. Members enjoy discounted registration for workshops, seminars, and events, along with discounted membership of FIB, opportunities for certification, career guidance, leadership roles, and enhanced professional recognition. IAStructE has its student chapters in several leading engineering institutions as well. Membership of IAStructE is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IAStructE is available on its website www.iastructe.co.in.
Vikas, shall I proceed?
Yes, sir.
Vikas, shall I proceed?
Yes, sir. Yes.
Dear friends, welcome to the webinar being held today. The topic is the story of longest span cantilever bridge in India, that is Bagchhal Bridge. The presenter is Engineer Sandeep Pattiwar. He is our Chairman, Professional Development, Indian Institute of Structural Engineers. And our moderator today is Engineer V.N. Heggade. He is former CEO of IAStructE, Executive Director of Gammons, and now founder of the Complete System. He has nearly 4 decades of experience in highways, bridges, energy, marine, and hydraulic structures. He is recipient of 16 national awards and an international award. He has over 170 publications and serves on key committees of Indian Road Congress, BIS, FIIB, and Indian Concrete Institute. He is also FNAE Fellow and noted for his advocacy of sustainability in construction. Now, over to Engineer Heggade for further proceedings.
Yeah, thank you, Dhawan Saab, for that kind words, and to get the sort of, introduction from you is an honor for me to start with.
Thank you.
Also, welcome to all the participants to this, what I call it as a SK Dhawan series of webinars, from organized by IAStructE, Indian Association of Structural Engineering. And today's topic is the story of longest span cantilever bridge of India. That is for Bagchhal Bridge. It's a very interesting story indeed. That's why we thought that would bring to your all of your knowledge. And the speaker is Mr. Sandeep Pattiwar. Sandeep Pattiwar it's an honor to, privilege to introduce Mr. Pattiwar, because he has worked with me for a long time, one of my favorites, to be precise. And he has more than 3 decades of experience in design and construction of bridges, all kinds of bridges, and special structures like chimneys also, and he was involved in the design of the marine structures also. So he's the right person to speak today, and he's right now the managing director or the director of Tech Solutions, which he formed the company almost around 15 years back, and well-established consultant. And this particular bridge he's going to talk about has already won 2 awards. Actually, this Bagchhal Bridge, for its design and construction also. His company has won that. He was involved in the design of this bridge, both when he was working in Gammon India Limited as a contractor side, and later when he became a consultant also, he gave he was involved in the design of this particular bridge, a very interesting bridge. in my opinion, in view of this latest IS 83, IS 80, like the seismic code revision, which is going to demand a lot of seismic retrofitting in many of the bridges is going to come. I think this could be a good case study for the seismic retrofitting of the bridges, because that's what I see that, and very going to be a very interesting talk indeed. And it's always pleasure to hear from Mr. Pattiwar. And incidentally, I was also involved in the design of these bridges on behalf of the Gammon, and to a certain extent in construction also. And but this bridge was completed after I left Gammon. It was a wonderful bridge which has been constructed by Gammon with so much complexities involved in it, and it has a story behind it, a very good story behind it. I'm sure Mr. Pattiwar is going to do justice to this story of longest bridge, cantilever bridge of India, that is Bagchhal Bridge. And Pattiwar, I think if you're ready, you can share your presentation
Yes, sir.
and start your presentation. The virtual podium is yours.
Yeah, thank you,
What
sir.
we can do is at the end of the presentation, if you people put the question and answer box, we will try to answer all those questions, which is there in the question and answer box. It is there. And if the time is short, we may take those questions which are important only. And with this, whatever, we are all set to go.
Okay, let me share this, my presentation to you. I hope we can see our presentation.
Yes, very well.
Thank you, Heggade sir. First of all, I'm honored to be you as a moderator, because I think no other than you can actually understand the conceptualization to the completion of this structure, which Bagchhal bridge especially, because a lot of efforts, I think it is not a one-person job, but it is a complete team who worked for this job, and is a marvel of now engineering, and that is what we are going to tell you, the story of the longest span cantilever bridge Bagchhal. So for timing, I will be video off so that there is a bandwidth is available. Now let us go to the first historical background. When we start any bridge, it is always start with a site investigation. We go to the visit the site, how it is there, and then only those ideas are always evolved that what kind of the bridge structure is there. It starts from the tender, and then after the tender again, geotechnical investigation, topography, all those studies done, and then depending on the construction, how we can do that structure, we decide concept on which the detailed design starts. If you see this photo, I think it is which a very picturesque location of the bridge. And despite the picturesque location is one part, but always civil engineer found in between the challenge of constructing, connecting the location from one part to the other, and that is what we call the bridge engineer, and that is he is the first to connect the network between the two sides of the people. So if you see here, this is something in location of P1. I think I will, yeah. So if you see, this is a P1 location, and this is typical 185-meter span. And if you see, this is a HFL of the Govind Sagar Dam. It is not HFL, but you can say that high um, uh, dam reservoir level. So at this location, this is a P2. The span is almost 185 meter, uh, and this site it is a 71-meter span, Maruttan site, and Swarghat site. As the hill is coming here, we could only stretch our span to 60 meter. So that was the initial configuration we have decided. So let us go to the history in the sense that when 185-meter, see one of the biggest cantilever bridge, when we suppose someone think about it, they think that how it should be done, what are the configuration, what kind of the pier should be there. First proposal was kind of the A-shaped structure, and the foundations were far apart here, if you can see, and the excavation planning thinking was developed that how this will be done. This is if you see, this founding level is almost 30 to 40 meter deep below, and cutting the rock, this was a kind of the shaft where the open foundation would rest, and then those pier, if you say the pier or tall pier, and then this superstructure you can see. The challenge was the water is available in most of the time of the year, and only 4 months were available for the construction of these foundations. And it was not feasible to provide uh, a kind of foundation where you need a lot of area to construct, and the seismic zone, as it is a 5, further seismic was getting increased, and foundation size were getting higher and higher with the stiffness of the structure. Geotechnical investigation was done. If you see, this is the founding level 460 was supposed to be go from 483. So almost it is 25 to 30 meter deep foundations were there. Construction started, planning was started. This is the location and level where the loose kind of the strata, and if you see the P1 strata and P2 strata is completely different. P1 has a lot of fractures, lot of rock which has a inclination in a different directions, whereas P2 crushing strength may be lesser, but it was almost more uniform than the P1. Geotechnical investigation derived the bearing capacity of both the strata at P1 and P2. And P2, in fact, it was 80 ton per meter square bearing capacity, and P1 it was 60 ton per meter square bearing capacity as per the geotechnical. Why I am saying this? This will have a future repercussion, and then we'll discuss it at that time later. Looking at the construction aspect, after the detailed planning, taking consultation from the site, it was decided a kind of shaft foundation, which is not normal in India, but maybe in a Europe. This is shaft foundation is a regular foundation type where it is uh, excavate up to the founding level, and the shaft is created in a rock of a uniform diameter. This has been done in India also, in a Chambal cable stay bridge, and similar in European countries. There are a lot of examples where such shaft foundations are done. They are typically uh, solid cylinder, having a aspect ratio preferably more than 2, that is 2 times of diameter. Now, if you see span is decided 60 meter, central span is 92.5 into 185 meter, and Morottan site 72.5 meter. Box structure at the top. This is plate pier. You can see very nominal thickness, even 2.3 meter. It will be look invisible from the far distance. And this is a kind of sharp foundation. When actually construction started, and there was a time period, duration, type of the rock, founding strata, and altogether it was decided that this foundation will be taken little bit higher. This rock profile which you can see in this photograph is actually for a construction became like this, and the site has constructed almost this foundation which is not as per the scale indicatively, and these piers were constructed. Cantilever of 58 meter on P1 side, cantilever on 43 meter on 42 meter side, 42 meter on P2 side by balanced cantilever method has been constructed. After a regular one site visit, when it was decided to go to the site for whether the construction, all those things is going as per the design or not, we went to site and inspected this foundation. We found that the depth or passive zone which is required, or the embedment location, or the resistance which it is required to take by this soil for this by the sharp foundation was not available. Red flag was given. It was decided together that this foundation should be stopped before further investigation to be done. All geotechnical investigation, then whatever the you can say the geo and structural investigation was required before further start of the further work. It was halted at that time, and then all kind of investigation, reboring, or whether we can do the salvaging of the foundation by the rock anchors, and all those measurements were taken so that this mass can be worked unified before failure of this foundation, so that this structure is safe for 100 years. Our various discussion from the experts, from IIT to the in-house or Gammon, I will say, for that matter, it was not concluded at any one point that this is a final solution, or by making a mass unified here or monolithic here, this foundation can be salvaged. Continuous construction and all efforts were taken to see that this bridge should start as soon as possible, because this was a very prestigious bridge for Himachal Pradesh also. Client has taken lot of efforts, and they continued the discussion is the best part to salvage this bridge. You can see the P1 is constructed almost around 50 meter, and P2 was almost 42 meter before it stopped in construction. The most challenging part, as you see, the foundation is much below the water, and to do the further any work, repair, we got only 4 months. Between that, we have to do the foundation. This is just a picture which has all grouting of the strata has been done to see that your geotechnical and structure can act in a one go or unified, so that this salvaging of the foundation can be done. as you see, actually, when it is 2013, when it has started to review, first of all, the condition at site was completely changed. Now, it was almost cut here. It was almost this topography was much flatter, and at Swargat also, the hill which was there is far away from the earlier AL. And proof consultant, we together decided that we should extend the span, at least should be symmetric from P1 to P2. That's why on a Swargat site, we have changed further increase of the 12.5 meter length. Generally, for a cantilever construction, when we say that we have a ratio of this front span and this back span is around 0.6 to 0.5. That is, suppose if it is a 180 meter, this should be 180 into 0.6. However, 72 was still not within that range. That was the maximum length we can stretch it. This is required. Why? Because when we do the cantilever construction, maximum load goes from P1 and P2 because they are cantilever, one side this cantilever, another side this cantilever. So they go load symmetric on this foundation. Joining of this foundation, after the balanced cantilever, some stretch is done on a staging at the end before the cantilever is done. So very less load is available at this abutment location, and that is why for continuous up to avoid the uplift at the abutment, it is always preferable that this length is little bit higher than the balance length. So after the deliberation, this is a final general arrangement drawing. You can see the salvaging of the foundation at P1 is done as shown here. It is by the rock anchors, and at P2, it is done by the pile foundation. Again, span is increased here from AL to A0. So abutment is no more at AL, but is transferred to A0 at an increase of 12.5 meter length. So spans are now almost symmetric, 72.5 meter Swargat side, Maruttan side also 72.5 meter, and central span is 185 meter. Any rehabilitation or any start of the activity, again, this core test is very important part. So when we went to site after a gap of almost 7-8 years, we decided that we should do the core test at different location of pier, superstructure, and abutment, which was already done, box kind of the abutment, which was already done on a Swargat site, that this core test should be done. So we have taken this core test, and results were fabulous in the sense all results were exceed than expectation, whether it is a carbonation test, whether it is a rebound hammer test, whether it is a core test result and alkali silica reaction test for a reinforcement or half cell potential test result for reinforcement, all pass with a flying colors. So uh, despite a very remote site, quality control was the best, I will say, at this location. Let us understand external pre-stress before we further discuss about the bridge rehabilitation, retrofittation, or salvaging. Typically, when we do suppose if there is one beam if it is a beam, and if there is a vertical load in this direction, it will deflect downward. But pre-stress component, if it is there upward, it will go upward. So that is a concept of the pre-stress. I will say that it opposes the direction of the dead load at whatever the general moments are coming. So if it is a downward moment, it will up the structure, and if it is upward moment, it will down the structure. In a cantilever structure, both phenomena happens, and that utilization of external pre-stressing we have to do it. There are some advantages of the external and internal. Apart from external, we have to be very careful, as this is not embedded in the concrete. There is a sensitivity of corrosion. However, it always can be tackled by changing the grout, or other measures can be taken. Main advantage of external pre-stressing, that these cables are outside, and you can actually reduce the pre-stressing force because friction less and wobble coefficients are little lesser. That gives some advantages. You can reduce the thickness of the member. That was the most important reason why we have decided external pre-stressing should be used for this Bagchhal bridge having a 185-meter span. When we were finalizing the I will come to the little later. See, let us understand first external pre-stressing. What is that? Actually, when we say extra dose bridge, it is a kind of external pre-stressing. The only difference in external pre-stressing, when the pre-stress is within the depth of the box, it is external pre-stressing, and when it is above the bridge boundary, it is called extra dose. So that is a major difference between the external pre-stressing and extra dose, because extra dose, it means we are giving a more power to the structure by the same cable. That's the philosophy. So it is not that Bagchhal bridge was the first kind of its bridge where the external pre-stressing was used. You can see in 1926, Basin and Railway Bridge in Germany has been used external bridge concept. As you can see, this we can call whether it is a extradose or whether it is a external. This is only a difference of terminology, but purpose remains same. That we are giving extra power to the structure, and it is not embedded in the concrete, and giving a more power to the to resist the moments. Typically, this all inclined tendons, and apart with the inclined tendons, you can see the external tendons are deviating from top to bottom. Advantage is that the same cables can be utilized from external to the bottom movement, and little bit reduction, little bit as per the deviation of the moments and the forces, this can be taken by the deviator. Generally, the deviators are placed at a location where the cable need to be change its path, unlike in a our regular internal internal cable bridge. We are taking those cable inside the structure and not outside. So that is very important difference, that this deviators has to be designed for this deviation which is coming arising out of the deviation of the cables to take the different kind of the moments and forces. Now, if we, after the external pre-stressing, let us understand when we have done the site visit, first thing we have done it is the change of the abutment location. So, to that was the earlier arrangement. You can see that it should be hold down by the pre-stress mechanism. And when we reviewed it further, because this length is very small, maybe 5 or 6 meter, so pre-stress doesn't work in this shorter length. Either you have to do the other kind of high tension bars or something other kind of thing. But we thought sustained uplift will cause a fatigue and not a good idea to provide such mechanism for 100 years for such important pitch. And then it is by balancing the structure or increasing the arm little bit more, it is simple uh, abutment with a bearings, and whatever the shortcoming of the load was there to safeguard uplift under the non-frequent load, I will say, because see, under the frequent load, uplift was avoided, and under the rare load and all those things, it is allowed. So that kind of the bearings have been placed. Despite that, actually at one location at P1, we could not avoid the complete uplift in a frequent load, that is under the combination of wind, and we have provided special bearings to resist this uplift for 100 years lifetime of structure. So you can see the earlier abutment was at AL, and the road was almost 90-degree taken during the earlier concept. However, this hill after the when the rehabilitation started, actually this hill is little bit far away. So 12.5 meter length is increased, and this road is contoured in a highway guidelines, and as best possible we have uh, designed this path. So you the special one thing to be mentioned here, typically we provide an expansion joint like this in a transverse location or the transverse section of the bridge, but we need to provide expansion joint along the longitudinal path. So they were going simultaneously, and the same movement which is coming, say, for here, maybe 100 mm, 120 mm was required for this phase also. And that was actually a big challenge, how to provide a expansion joint in such a way that it should work very nicely. Let us go to the salvaging of foundations. So you can see the picture of this P2. I think geotechnical engineer think in a different manner, and bridge engineer think in a different manner, that how this forces has to be transferred. And combination of both is always required to decide what is the course, what is the action, what is how to decide it. Always, if I review, always there was a geotechnically they were always concerned about the P1, whereas for a bridge engineer, our concern always was P2 and not the P1. So you can see uh, whatever the mass which is required for the mobilization of P2 shaft, which is not transferring by way of uh, from the base, those forces, but taking a resistance from the side was not available at P2 location. Maybe the soil, strata, rock, which we thought is good geotechnically, could not sustain one one cycle of the water variation, and that's why we thought we have to review this the foundation. P1, as I said earlier, it is a number of rock anchors. Now, at this time, we have decided let us not compromise on the founding level. So we have to transfer those forces at a much deeper foundation. So that is why this rock anchors were given, and those minimum forces were given in such a way that it is P by M by Z is okay, and these forces have been transferred from pier to the mass below. One challenge was rock anchors, and second challenge, how to connect this rock anchors to already constructed pier. See, if you see here, the core, central core, which is here, is already constructed, and this outer core is to be done to make it monolithic with foundation, with pier and this rock anchors. So first the rock anchors were drilled, and then this jacketing part you can see at the foundation, so that this whole design was done in such a way that they can take this forces and transfer to the much below strata, lower strata or deeper strata. So this is indicatively after the construction. You can see that this is the outer mass, outer jacketing, which is holding this foundation at the bottom. Rock anchors were decided in such a way that these forces, moments, lever arm can be transferred into deeper action. So in a blue, we can see the pier, and the yellow color we can see as a jacketing. So that way, that is why these rock anchors are made monolithic with the pier foundation. The challenge was again always with a month and duration of time. So we have to do all those things parallel activity, not only for P1 but for the P2, for the because only the 4 months were available. All geotechnical stiffnesses and were considered. Plaxis and all those things softwares were used, where the geotechnical and structural interaction was used and done to see whether these forces can be transferred to the deeper strata from the pier and shaft foundation. Next challenge is actually the pier which is already done, and now if we want to do the jacketing, how to avoid the reinforcement. So special experts were called, and they have scanned the reinforcement before drilling the each bar. And again, we don't want it to make the pier very weak in a cross section. So care was taken that all holes in a one row will not be drilled together. If it is required, maybe in a column, but set of guidance have been given so that once the bar is drilled, it has to be grouted so that active load which is coming on this pier, as the cantilever already constructed on those piers, the load capacity should not reduce. So it has a capacity, but we don't want it to take advantage of that. Minimum 500 mm length, maybe again those rock anchors requirement are comes very less, but minimum requirement was given. And if it is more as per those chemical grouting or different anchors are there, if it is more, then it is should be more. Otherwise 500 minimum have been provided. So you can see here, I will come to the next slide, which is in P2, much denser foundation reinforcement is there, and it was much bigger challenge at the P2 side. So if you see the P2, which is the as per us, which is the most critical foundation, where we have to transfer the load in a deeper foundation from the shaft foundation, which is not fitting into the aspect ratio, not transferring the lateral moment, socketing moment. Pile foundation was decided to transfer the forces. Now that is easy to say pile foundation. If you see here, it is a shaft foundation, and it is a series of the piles along the periphery of the circular shaft, and this is the pier which you can see in a plan. Now, most challenging part, how to connect this pile cap to the already existing pier so that all moments are transferred. It was deliberated for long that how whether the contribution of the shaft foundation, which is also exist here, whether it will take the load or not. All geotechnical calculation, resistance, but it is ultimately decided if these piles are embedded much deeper, they are much rigid, and the purpose, if the soil underneath the short foundation become loose, all load will go to the pipe. And we have finally considered that even existing this short foundation's load, even if the soil underneath go away, this foundation, pile foundation can take that load and transfer the load into the deeper strata. So that is why the foundations were designed and integrated into the pier in such a way that all loads can be taken safely. So this is a typical foundation drawing. This is not need not be very. Now you can see its site here, and you can see the design here. See, it is a hexagonal kind of the shape of the pile cap. Piles are shown here, and these cables are there. Now you imagine that shaft which is already constructed, and we have to drill the holes from already cast pier, avoiding the reinforcement, and that is this is not something 1 meter or 0.5 meter. It is almost 2.6 meter at this location, and all scanner and digitalization or modern tools were used to see this reinforcement cutting can be avoided, and according to that, continuous interaction with the site was done so that pier is drilled, and as less possible the drilling in a pier is done, and other cables were done placed outside so that uh, uh, those clashing can be avoided. So you can see 1, 2, 3, 4, these cables are going through the piers, and other pre-stresses is going outside. Apart from that, your shear reinforcement and all those things were all were there. So you can see the pockets either here in a cables, and at side uh, it is very visible. In fact, this pile cap uh, uh, was not done in a complete one operation because there was a sudden water has come. So it was done in a water season, but it was done completely successfully. So this is indicative just sketches showing that how this drill and all those things was done. Jacketing was done. And here this jacketing and all those things, this shear connector was provided on the face of the pier before casting this pile cap. Now you can see the shaft, which also the pile cap and this pile. So it means the shaft, first load is going to the pile cap and then to the pile. And it looks like that it is hanging on the pile cap and then going to the pile. This load itself was around, if I remember properly, it was not very less, but something around 700 to 800 ton. And then see, more than the other loads, it was also very heavy load for design of pile foundation. Now, after the foundation, the pier rehabilitation was started. See, you can see I will say the mass scaffolding. It was done up to the height of 30 to 40 meter, stage by stage. All jacketing of the pier was done from all the side. Again, classic formula is used. This pier, at this stage, I will say that, see, if you look at the bridge, when the bridge was started designing, it was a working stress method. And when finally salvaging was decided, it was by the new code, which is limit state method. So those piers were checked for the limit state method, and it was decided to do the jacketing. So jacketing, you can see, uh, uh, again, typically SAY bar upon IB is a conventional formula, whether it can be any derivation can be there, but by that method, all uh, uh, difference of the forces which is the pier which is taking, and then further jacketing, how much movement and forces will come here at this interface were calculated, and this shear connectors have been provided. So that is again done throughout the depth for all combination, whether it is a seismic combination or any combination, but only difference that it was done as per the new code, which is limit state code. Now, another challenge was, see, we have strengthened the pier. We have jacketed the pier. We have to connect throughout this superstructure. Otherwise, the purpose of jacketing will not be there. And already superstructure was also completed for certain length, maybe 40 meter for P2 or 50 meter for P1. So how to do that? Again, see if you see in a longer direction, the forces are transferring in a different manner. So again, in a transfer direction, you can see this web is thickened up to the top, but whereas in a other direction, uh, hole was drilled through the soffit, and whole thing was made monolithic in a elevation. If you see, it is going up to the half of the web, whereas in the transfer direction, it is going up to the full height of the web. So this is, you can see the reinforcement, which is going, see, because all movement which is required has to go from this section. So already soffit is cast. So we have to bend the bar like this, maybe not exceeding 1:6 or 1:8, and then made a hole here, each one by one, so that we don't compromise on the strength of the box, and then it is taken up to the top, and then it is jacketed. Now, with the change in the superstructure configuration, so earlier it was 60 meter, then again it is 12.2 meter. The forces, creep, shrinkage at a different stages are coming now, because see, already the construction is over now, and now the new construction will be happening. So those difference of the age at P1 and P2 has to be considered as per its stage of the construction. So all those rigorous analysis was done, and then it is adopted. That is one thing. But main thing that these are the internal cables. You can see that this cantilever, if it is start from the P1 and P2, your typical cantilever cables happens balance for a balanced cantilever construction, maybe 3 meter here, so 3 meter here, another length of the segment here, so another length of segment here. Typically, it is safeguard the cantilever required for the dead load, and then the remaining load, if it is coming, that also it should taken care. So that is a profile of the uh, cantilever cables. And same here, if it is a continuity, so continuous continuity cables are placed here at the bottom, and uh, the creep something which is a phenomena that it relax. I will say that I just take a parallel with a, suppose a person who is sleeping here. Maybe at initially he will resist to transfer the load from between P1 to P2, but after some time his back will start going slowly down, and that's why that is where this bottom fiber also will take into the tension. So that is I take a parallel of the creep load. So that's exactly happen in a cantilever structure. Though we are designing the cantilever as a cantilever method, so load should ideally go as a cantilever and then down below to the pier. Load goes as a pier only, but the bending moment start reducing for a dead load, and this reduction in the bending moment at the cantilever increases the bending moment at this part, and that is what we call creep phenomena for indeterminate structure. This is the internal cable profile. Of course, a lot of cables are going from one point to the other point, and all care typically profile is done in such a way that they don't clash each other. They have a radius, deviation radius is so that it is not exceeding the limits, so that no additional reinforcement is required to provided. If you see here, actually, the reason of external cable, provision of the external cable was that if we provide all internal cables, thickness of the member were increasing so high that it was a cycle that if we increase the bending moment because of the permanent load, number of cables will be go on increasing and increasing. So that's why it was decided why we should not provide a combination of pre-stress cable. One part is internal cable and another part is external cable, so that for the dead load construction, at least this internal cables can take care. Maybe there is some residual still remaining, and we will add the external pre-stressing by by not increasing the thickness of the members at the top and the bottom, and take advantage of the, take a profile in such a way that where the continuity cable, where the demand is required at the bottom, we can deviate this cable at the bottom. Where the demand is more at the top, we can deviate this cable at the top. So that is the beauty of the external cable. We can do it very easily. So that is why we have decided the combination of internal and external pre-stress and uh, the provided profile. This is again a modeling photograph. So fine, if you can see and imagine, if we would not have provided these 4 cables, dead load will go on increasing, and that it would have been very difficult to uh, take the design the bridge. I think, see, almost when we did the first trial, my cables were coming almost in a 2 rows at the bottom of these layers. All this part was full of cables if I would have used the internal cables. So either I have to increase the web thickness or either deck thickness or something. And again, the CG of the pre-stressing cable were reducing quite a lot. I think you can see the this deviators here. the location of the cables from where external cable will uh, go in and come out in other side, and then further will go to the location where it is deviators are placed. So here you can see the central diaphragm from these cables are coming at the top here, and then again a next deviator, they are located in such a way that whatever the demand is there according to these cables are deviating from at that location. Uh, in any external cables, say in a internal cables, your cables are inside, so those deviation doesn't happen in such in a as external force, because difference of the cable after the grout in an internal cable is any deviation or any bending of the member happens, this force in a cable will increase, which is a itself is a opposing the normal phenomena. That means it cannot happen, in the sense your self balancing system should be remain, or in a cable failure condition happen, mechanism happen if my cable forces are reducing, then only this bending will happen. But in an internal cable doesn't happen that way. So that is why uh, in internal cable we don't calculate the deviation of the forces in a cable, whereas in an external cable you will have a deviation in a plan or elevation, something kind of this deviation, and this force uh, 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 will come, and for that you have to provide a detailing in a properly to take care of this. One is the force and second is the shear. So all those things you can see that if suppose I have multiple cables, then how much force will be coming on a web where I have to again make it integrate with the members, and then I have to provide the reinforcement accordingly. Again, you can see some location we have anchored. I think this is opposite of the anchorage. It means in the sense that this cable is going from here and anchoring at the back of this deviator. So one cable is getting anchored here because this demand is not required, or those cables which we have provided is overlapping each other. So this is the detailing you can see, or the actual photograph you can see. Maybe this is a design drawing design drawing, and this is a photograph where they have anchored, where they have pre-stressed the cables from other side of this diaphragm. Regular stresses check, I think uh, everyone is aware that, okay, this is cantilever construction. So bending moment develops as a cantilever. Each segment by segment, this moment will go on increasing. Typically, cantilever moment with a uniform distributed load, like what happens. And though it is shown as a one line, but we have to take always condition where the one segment and one launcher is on one side, and unbalanced condition also need to be checked for the pier and for superstructure. So now you can see the photograph where the first this is part, now jacketing and all those things is done, and the further construction is in progress. Once the cantilever construction is complete, actually earlier we earlier in our case we have provided a one trussel here, so that deflection, deformation and all those things is within okay. So that was continued here also. So cantilever construction, you can see this is a support here. It was a support during the construction, and the bending moment is coming in this fashion, in this manner during the construction. So this is a dead load moment. Of course, pre-stress will be uh, determined until unless there is no other third support, because this is already the monolithic. As soon as you place another support, the structure will become from determinate to indeterminate. Again, the indeterminate structures pre-stress will be different, and that will start acting on that. So this is the pre-stress bending moment you can see. If suppose this is if this is would have been cantilever structure, this reversal of the action would not have happened. But as maybe cables are like this, here it is again, support is there, so your pre-stress moments are coming in a different manner. Now finally, one is the ultimate capacity, which you have to check it again by reinforcement. As I said, the superstructure was designed as per the working stress method. Now, when we say in a working stress method, difference in a limit state method is that in a limit state method, we can take tension up to the flexural strength of the concrete, whereas as per the earlier working stress method, except temperature, all other in all other condition, tension will not be allowed. So that was the major division we have observed for this bridge. However, as we have decided that this superstructure will be designed for working stress method, and again, yield of ULS method was calculated as per the earlier code, and by yield of steel and crushing of concrete, generally, whatever happens. Only point to be mentioned here, external pre-stress doesn't act like a pre-stress. So when we'll calculate the capacity, uh, external pre-stress will behave as a external force and not the part of the pre-stress. So the calculation will be slightly different. This creep and shrinkage diagram, any software simulation is done. So this is the before the stitch, I will say. See, all your construction, cantilever construction is complete. Then your abutment and the piers are over. And then this central part is taken a cantilever method. And just before the stitch, this is a stitch diagram for primary moment, pre-stress moment, and all other secondary moments and all those things. So this is after stitch. Now this bending diagram you can see, because there will be some internal cables and there is some external cables. So all those conditions, the pre-stress moments, stresses, and all those things will happen. Here it is the stress diagram due to dead load plus pre-stress at the top. So everything is positive. Minus is below the line is positive, and here also at bottom. I think this diagram is much clear that stresses under the basic condition, we do not have any tension at any location throughout the length of the bridge. However, we have provided a untension reinforcement at this zone because the stresses under the temperature were below exceeding the 0. So that was not allowed, and reinforcement which have been provided in the deck, soffit, and all the section, the reinforcement has been provided. So if it is a if it is a tension in top, you have to provide a reinforcement at the top to take care of the tension reinforcement. If it is a bottom, you have to take care of the reinforcement for the bottom. Stresses under seismic condition. So This is also almost not going below 0. Another new thing for us, see when we provide a internal cables, those cables are uh, very smooth. It is going inside. It is following the profile. However, when there is a deviator and for external cable, when these cables will be placed like that, it will try to deviate maybe with a different condition. So if we don't put a deviator, see, you can see the deviator here. So it has a certain radius which is given in the PTI manual here also. So that this cable when come out, it should not uh, uh, grip and friction should not happen, and it should not go in a fatigue. That's the idea, that a sampark cone is formed by the steel tube, and this profile is done according to PTI manual for all external cables. I have already explained, but this is a sketch showing the type of expansion joint. This expansion joint is type A is different and type B is different because it has a longitudinal movement as well as the transverse movement, which is very less. And this dedicatedly is a axial longitudinal movement only. Bearings, uh, free bearings in both this direction and guided bearing in this direction. Of course, P1 and P2 is monolithic. This I am talking about the AL and AR. I would like to say, this is again, I will say that it is teamwork. See, everybody has contributed from PWD, Himachal Pradesh, Gammon, of course, IIT Roorkee, B&S Engine Consultant Private Limited, who were our proof check, and Tech Engine Solutions. There are some references we have given so that if any engineer want to understand further direction or any guidance, they can just go through this references also. Thank you. Thank you very much. I hope, I'm not sure, but I hope I have done the justice to the story of the Bagchhal Bridge.
Thank you. Thank you.
1 second, sir.
Yeah. I think if you can just share your
Yeah.
presentation, and now you can show yourself. I think it can just come.
Yes.
Very nice presentation. You have done justice to your presentation, as you said. And one has to understand this particular bridge that was conceived. There were a lot of constraints. Because of the constraints, as you can see, that the bridge was to be conceived as an asymmetrical bridge. On one side, only 62.5, and the another side, 72.5 cantilever was provided. Because on the one side, the hill was very near, as rightly said. Over the period, the hill was basically, eroded, and there was sufficient space to extend the span to make it symmetrical on either side, 72 and 72. That's why during the conception, it was only 65 or 62.5.
60 meters.
60 meter. And another constraint really was the location of the foundation itself, because 185 meter span was done, and extensive geotechnical investigation was also done. And after doing the extensive investigation, geotechnical investigation, it's not only that the third party, good geotechnical agency was done it. Even the geological studies also was done by the geologist. Basically, after having done that, the foundation location was decided. The major constraint was again that it was a backwater of a dam. Basically, the backwater of a dam, and most of the time, the standing water used to be there, almost around 15 to 20 meter depth. Water used to be there. So the working season for the foundation was only 3 months, though it is water was receding 3.5 months to 4 months, but both the foundations were to be completed were to be completed within 3 months, and the overall contract period was 24 months. This job was contract period was 24 months, as you are aware of it. With this, also to reach the location of the foundation, there was no way we could have, like managed to take the pile foundations. Say, for example, if it is to be conceived as a pile foundation, we'll have to take the RCD rigs, because the piles were to be done in basically in rocky strata, and almost around 12 piles, as you can see here, of 1.2 meter dia, was to be done, as you can see in the revised foundation, almost 1.2
Uh,
meter. It was almost,
I know, I know. It's a
it's
good one.
almost possible
You
task.
are also,
I think
I
just,
am
just
sending.
mute, Mr. Dava. Yeah, almost impossible task to do the foundation within 3 months and complete the contract within 24 months. Under such circumstances, after having done the extensive geotechnical investigation as well as the geological studies by the geologists, basically it was decided basically to see that the excavated shaft, similar to that of the drill shaft kind of foundation, was adopted. And with this constraint, when this was adopted, basically, I think we went ahead with the design and construction, and the design was approved. The design was completely approved by IIT Roorkee at that particular point of time, after having gone into the depth of everything, and also again it was to be totally scrutinized by the clients themselves. So this bridge was completed, and was in progress as per the schedule till I think the geotechnical surprise was encountered at that particular point of time. After the first season, and the water receded, and we had to continue with the work, and it was seen that the one side of the foundation, especially on the P2 side, the eroded, like the one side of, so on the basis of the rocky stratum, actually the socket resistant, it was designed as an excavated shaft. When you say an excavated shaft, the bearing capacity is decided on the basis of the principles of the socketed rock, socketed shaft. When you say the socketed shaft, a shaft is socketed into the rock, and you get the not only the end bearing pressure, end bearing capacity, but also by the side resistance. Side resistance also you get as you calculate the socket resistance of the pile which is socketed into the rock normally. That is how it was calculated. So, but the geotechnical surprise was encountered, and the solution was to be given. Now the question comes again. And then, after having done all the investigation, actually, the the structural configuration of the bridge itself, it was made symmetrical, and as Mr. Pattiwar explained at the end, like that uplift abutment configuration was changed by putting the mass concrete into the superstructure. When you do all these things in the revised analysis, it required a thickness of the pier to be increased. That is why you see the jacketing. I think that point was not highlighted by Mr. Pattiwar, because whole the stiffness of the bridge, whole the configuration of the bridge is done, changed. So the revised analysis indicated that the thickness of the pier which was provided was not sufficient. So jacketing was to be done. Then we had on the one side where Mr. Pattiwar explained, on the P1 side, I think from the geotechnical engineers and the geological engineers consideration, P1 side was critical. But when we really did that analysis and kind of thing, we found out that the P1 was not critical and the P2 was critical. So I think the point which was made by, I think it's a combined efforts of the structural engineer as well as the geotechnical and geological engineers. If all these geological engineers, geotechnical engineers, as well as the structural engineers look at the problems independently, like if geotechnical engineers is only worried about the soil bearing capacity and how the structure is going to behave without understanding. I think if some people, different engineers are working in a compartmental and island way, I think this sort of problems will be encountered. Now, this is how this is the story. In fact, all these things you see in between, the work was stopped. After the work is the cantilevers on the P1 and P2 progressed to the certain lengths, as Mr. Pattiwar explained. On one side, 52-meter, another side, around 40-meter, cantilever construction was done. Work was stopped, and the hiatus was 8 years was there in between. 8 years hiatus, in the sense the gap to start the work again after the doing all the investigations and coming to a proper solution. So 8 years was there. And the quality of the construction when the NDT testing was done, including the partial NDT testing, partial non-destructive testing, like core testing was done, it was found that the quality of the construction was fantastic. The concrete quality was very good, at that remote location. That is a plus point. And even for doing the pile foundation also, I think somebody has asked a question, why not the pile foundation? In the revised proposal, we have got an integrated pile foundation with the excavated shaft foundation. Of course, the shaft was redundant in the revised design. It was not taking any load, though already some of the loads have already passed through it. That is the sharing between the shaft as well as the piles was a difficult way to calculate how much load goes there, because already locked up pressure is there in the shaft foundation, whether you like it or not. 40-meter, 45-meter cantilever is done, and that load is already transferred to the shaft foundation down. But in the final analysis, that was neglected. The load transfer to the shaft was neglected, and it was done. Even to take the pile rigs, that is an RCD rig, and to making the way for the RCD rig to the pile location, there were 12 piles, and it took 2 to 3 seasons. So that is the reason. That is the reason initially that the pile foundation was not envisaged. The excavated shaft foundation was conceived on the basis of the geotechnical and the geological studies. So with this, I think the question of why not pile foundation in the initial stages can be is answered that way. And if you permit me, Dhawan Saba, I'll just go through some of the questions which is there. I think which Pattiwar can answer those questions. Not many questions are there, of course. And I have already explained why pile foundation was not considered. And I think, Pattiwar, you can take these questions if you want. But Bhaskar Sen is asking, what are regular future maintenance activity and periodicity and tool, if any, whose scope it is? It's a client scope, basically.
Yeah.
Client scope, Himachal Pradesh PWD scope it is in. And I think they are having a maintenance manual. I think all the bridges these days, which is constructed on the PWDs or by the NHA after the completion of the job, I think the maintenance manual has to be given. Accordingly, it has to be followed.
True, sir.
Sandeep Deshpande is asking, pricing existing footing, piercing perhaps he's saying, mean the existing footing is completely ignored completely. In fact, I take the liberty to answer that question.
Yes, sir. Quite.
You see, after the work was stopped for almost 6 to 7 years, Dr. Raina's intervention was also there in this project.
Yeah. Yes.
I think Dr. Raina also gave the micropiles, like the micropiles to be piercing through the existing foundation instead of on the P1 side, the rock anchors, precious concrete rock anchors, which was provided was sufficient. There was not much problem. On the P2 side, Dr. Raina gave the proposal of the micropiles piercing through the existing shaft foundation and taking the micropiles to the 30-meter depth instead of pile foundation he had proposed. But when you say micro piles, it is around 300 dia piles. But as per the contract for the river bridges, the micro piles were not, permitted. That is the reason instead of micro piles, we have, I think the contractor had to go for go for the regular piles. The regular piles is not pierced through the existing shaft. Regular piles is at the periphery, outside the existing shaft, and on top of that, the pile cap is constructed. Pile cap is integrated with the piers, existing pier, through the pre-stressing, and some of the reinforcement, 30% of the reinforcement passing through the pier, and the cap is pre-stressed together. That's how it is done. And Mohak Nagarani is asking, why was pile foundation not considered during the initial planning stage? I think that I've answered that question. Again, Mohak Nagarani is asking, how was shear reinforcement anchored from the existing pier to the new pile cap? The pile cap has the shear reinforcement. The reinforcement, which is, like the pier cap, the pile cap, which is on top of the shaft foundation. Pile cap is right on top of the shaft foundation. Pile cap is pre-stressed, and the pre-stressing cables are going through the pier, existing pier, and it is sufficiently pre-stressed so that it is integrated with the pier properly. That's how the solution was found. Dr. Yogini Deshpande has asked, how was ASR test done on concrete? It is normally done on the virgin aggregate. The IS mentioned is also for aggregate and not concrete. No, when they say alkali silica reaction test, it is done on the aggregate only. Some of the concrete pieces were taken, and on the aggregate, the ASR alkali silica test. It's not done on the concrete. When I think maybe
it is chipped off. It is chipped off, and then from that sample, it is the testing was done.
ASR test is done on the aggregates only. Nagarani, what was the tender cost and final cost? I think the tender cost for such a bridge is only, I think it was around 20 crores, and the final cost also has not gone much. I think 25 crores. With the escalation only, that would have increased because of the 10 to 12 years. I don't think the cost has increased because of these changes in the foundation. Arun Mohan Kumar, sir, due to unsymmetry of bridge, did you experience any issue in geometry controls? Also, did you try to provide horizontal jacking at the superstructure, compensate founding forces? I don't think so. I think, Pattiwar, you can take that.
No. See, jacketing is done for some other part. Now there is a challenge of the joining two structure for a different time. So the geometry control was done accordingly. Those modeling was done accordingly. So that P1, suppose if there is some gap, and efforts were taken that those cantilever units, when they meet at the central, they should come simultaneously and not staggered, so that we can control the geometry and regulate and monitor the site, so that they can come and lock the things properly. So that was the precaution we have taken while constructing the cantilever.
So I think that should satisfy Mr. Mohan Kumar. And Kulkarni is asking, Sriram Kulkarni, why pier jacketing was required. I explained, Mr. Kulkarni, actually the structural configuration of the bridge itself was different. We had increased on the one side by 60 to another 12.5 meter. And also the mass concreting was put inside on the one side. The reanalysis required the jacketing of the piers. That's why it was done. And SK Nazrul Islam is asking whether 10 in long column effect was considered from top or drill shaft or from fixity point of drill shaft socket position. I think I didn't understand. Pattiwar,
I think he is talking about the pile foundation. When it is say under the scour condition, it is a free length is taken. But if it is embedded in the soil continuously, in our case P1 and P2, both foundations are from the top. So there is no scour as such, because this flow of the water is not, this is upstream of the dam. So there is a ponding of the water. So scouring action doesn't happen here. And further, all piles are actually socketed in the rock from the top. So there is no question of the second order effect to be considered in a pile foundation. But for piers, yes, it has been taken as per its um, effective length and all those things are the geometric condition. Geometric condition.
Thank you, Pattiwar. That has been an exciting, in fact, presentation, and you have told the story of longest span cantilever bridge of India. Thank you for that.
I just want to add, see, suppose someone has asked about the spile foundation, why it was not adopted. See, actually, this technology or the modern tools doesn't start from the beginning. In fact, when we have started the pile foundation, strata was so difficult, it was not possible to do the piling on that strata. Now the question comes that how we have done it now. See, actually, the method, machines, tools which has been used for the signature bridge, which a special mechanism has been brought it. Same machines were actually brought at the location. Small diameter holes first drilled through in a rock before the RCD piling machine was activated. Those framework and all those things was placed at a site, and then those piling was done. Though it was that may not have been possible at the start of our bridge. So again, the change of the machines, equipment also has made impact while the salvaging of these foundations.
So I think another interesting question I see in the chat box, not in the question and answer box, that Arnab Adhikari has asked why P2 was critical. That's a very interesting question. See, on the basis of the geotechnical and geological condition, on both sides, investigation on both sides, the shaft foundation was conceived. And on the P1 side, whatever the assumption, whatever the geotechnical investigation and geological investigation results were given, that was matching with the existing condition. Though there was a precious concrete anchors, that was done only from the point of view of additional safety. In fact, there in the P1 side, nothing was required to be done on the basis of the analysis and the design. But on the other hand, on the P2 side, the actual strata which was encountered, it was not a strata which was giving the socket resistance to the shaft, basically, because the side resistance was not available. That is why the P2 was critical. I think with this, I would like to hand over the podium to Mr. Dhawan for his final remarks and conclusion of today's webinar. I think you have to unmute, Dhawan sir. Unmute yourself.
Excellent presentation. I would say many new things have emerged. So before concluding, two things I would like to ask. This life of bridge, he said after this retrofit would be another 100 years. Any mechanism of, putting sensors and monitoring this, how that will be done? This is my just simple query.
See, our philosophy of the design that if we take care of the cover or whatever the as per the exposure condition, if we are meeting those requirement and specification, our bridge should stand for the 100 years. Yes, regular maintenance is very necessary, that any deviation other than what have been considered in design is happening at site or not. So I think as of I know, I don't think any instrumentation and all those things PWD has decided as of now, but we can suggest that if it comes to that level, we can think and then what are the critical points which has to be measured, we can suggest to them and this instrumentation can be done, certainly.
Otherwise,
I think Heggade Sahab has any other view? for regarding this, I think he can.
No, I think you please carry on, Dhawan sir.
Okay, sir.
I would say, I mean, very nicely explained, and I think the persons who are the participants must have gained enough information and motivation, because dealing anything with the existing structures, I think is more difficult than constructing a new bridge.
Yeah, true. Very
And then
true.
with so many changes, right from the foundation to the piers and to the superstructure, is really, I mean, design and construction, both the things are really, I mean, challenging, and then it has been done satisfactorily. So thank you to speaker and the moderator. And now next month, the new topic, the new subject will emerge, and that will continue. So thanks to everybody.
Thanks, sir.
And then now we can conclude. Thank you.
Thank you very much.
Thank you. Thank you very much, sir. Thank you.